So hello again. So before we continue with our discussion of the electric field, let's step back for a moment and make sure you guys have a general idea of fields are. So let's pause for the thinker question over here. The question is very simple. At 6 inches in front of my nose, this point in space, write down every field that you can think of. So just to get you started, temperature is a field. It's measured with a thermometer like this one over here. So if I hold this at this distance over here, I can read the temperature. And that appears to be something like 74 Fahrenheit, 24, 25 Celsius. Nice and toasty, basically. So think of all the other fields, properties of space and time. The physical quantity, that's a point function. Just to remind you, a field is a physical quantity that's a point function of space and time. So temperature is one example. Think of every other physical property you can think of. That's a function of the location and the time. Okay, so here's a list of some. So air pressure, air density, temperature we already talked about. Air velocity, the air could be moving over here. There could be a bit of a breeze. So that velocity is it's a field. It has different values at different places. It changes with time. Gravitational field. If you hold something over here in front of my nose, watch this thing getting pulled down. There's a gravitational field. There's a magnetic field. The Earth produces a magnetic field. So you can use one of these things. This is an old-fashioned magnetic compass. And with this, you can detect the direction of the magnetic field. So these are some examples of fields. So a field is any physical quantity that's a function of space and time. It's a distribution, basically. So now with this sort of a brief commercial interruption, let's get back to what we were discussing earlier, which is specifically electric fields. Okay, so here's the question to you. This is the charge comb that you've seen earlier. Here's a point in space. How do you detect the electric field at this point, and how do you measure it? How do you put a number on the electric field over here? So see if you can come up with a simple experiment for that. So this is another one of those thinker questions. And pause the video briefly, see if you can come up with an answer before I discuss it. Okay, so the quintessential property of an electric field is that it exerts a force on a charge. So the way to test for an electric field is with a charge. So let's say we are trying to find the electric field over here. You put a little charge over here, and you watch that thing getting pushed away. You see, put the charge here, watch that thing accelerate away. So the direction of that acceleration, let's say it's in this direction. The direction of the acceleration, that gives you an indication of the direction of the electric field. So I put a positive charge, suppose it's 3 coulombs, measure the acceleration. Since if you know the mass of this, you know the force. It's also in this direction. So you've measured the force on a charge at a point in space. And then by definition, the electric field times the charge, that's equal to force. And so this is how you detect and measure an electric field. So you have the basic force equation, F is equal to E times Q, this little q over here in this case. So therefore, the E in magnitude will equal the force divided by the Q. So this Q is the 3 coulombs, the force is whatever it is, measure that force, and putting these things together, that gives you the electric field. And the direction of the electric field, if it's a positive charge, it's in the same direction as the force and the acceleration. Okay, so the next order of business is electric field lines. Now, before getting into the lines of electric field, let's look at something more familiar, such as wind. So in cartoons, anytime you have a vector field, it's common to draw these lines indicating the direction in which the stuff is flowing. In this case, wind. As you said earlier, wind is a vector field. It's a field. It has a different value at different places and different time. It's a vector field because it also has direction. So anytime you have a vector field in cartoons, they show things like this. If the people are speaking loudly, they show like rays coming out of the mouth, something to that effect. So the same idea applies to the electric field. So you have something very similar with electric field and electric field line. Here you have a strong concentration of positive charge. So if you were to place another positive charge over here, it's going to feel a force away from it. If you put it over here, it's going to get pushed in this direction. So these red arrows here, they indicate the direction of the electric field. These are the field line. So a field line is basically like a locus of the force at different points in space. You look at the force over here, then you look at the force at the next point, and the next point, and so on. And that's basically what the electric field lines are. Now, the one thing you can notice is, as you go away from this positive charge, the electric field is going to get weaker. Correspondingly, these lines are farther apart. So as you get close to a charge where you have a high electric field concentration, the lines are more concentrated. As you go away, the electric field drops, and that's indicated by these field lines becoming more dilute. So the concentration of the field lines becomes an indication of how strong the field is. Here are some more examples of field line patterns. So on the leftmost thing over here, that's actually an indication of the field lines for a magnet. You see N over here is kind of hard to see, but that's the North Pole, this is the South Pole. This is a bar magnet. And you can visualize the magnetic field line by putting this under a piece of paper and sprinkling the paper with iron filings, fine magnetic dust. So that kind of gathers and around these field lines and indicates what the field lines are. It's a way to visualize it. Here is a diagram showing the electric field lines for two positive charges. Notice that the electric field lines sort of leave the positive charge, but they turn away from each other when they get close to the field lines of the other positive charge. And that's the reason you have repulsion between these two. The rightmost figure over here, you have a negative and a positive charge, something known as a dipole. And you can see that the negative charge, it's a sink for the field line. So the electric field enters the negative field line. It's like a vacuum. The positive charge over here, that's where the field lines are leaving from. So you end up with this pattern that basically looks like this. So these are a couple of examples of field line patterns. So in certain applications of this idea of field and field line, what really matters is the total number of those lines that you catch. What do I mean by that? Let's look at the situation where you have a sailboat with a small sail over here. So it's in a strong wind. So you have all of these field lines concentrated, closely packed together. And this small sail is able to catch enough of an impact. It feels a certain force. It gets pushed in this direction. Here you have a sailboat in a lighter wind, not as strong. So the field lines are far apart. They're not so concentrated. However, you can make up for it by having a bigger sail. So as a result, you have a force of the same magnitude. So in many situations, there's a trade-off between the area that's catching these field lines versus how concentrated these field lines are. And that is basically the concept of flux. The total number of field lines that you catch, that's the whole idea behind this physical quantity called flux. So in the sailboat example, the wind is exerting force and pushing the sailboat. The sail is catching that wind. That force is basically the flux. It's the strength of the wind multiplied by the area. So you can have a stronger wind and a smaller area, or a lighter wind and a bigger area. We are sort of catching the same impact in both cases. A further factor comes in, which is the orientation of the sail. So if you have wind coming at me and I hold this card like this, it's going to feel a certain push. If I hold this card like this, the wind will go right back. This is going to slice through the air. There's not going to be any push. That's why in sailing, a very important thing that you do is to orient the sail in the right manner possible. So the angle also matters. The bigger the area, the more the flux, the more the impact. The stronger the field, the higher the wind, obviously you're going to have a bigger force. but also how you orient the area so that it's facing that vector field. You want to make sure it's basically facing it head on. How do you express this? So what you do is you draw a normal to this area, and then if the field is in the same direction, that shows you'll have the maximum impact. Okay, so let's say the wind is coming this way. You want the sail to face the wind head on. And the way you do that is that the normal to the sail, it needs to be parallel to the wind. In that case, the area is facing the wind. So that's how the angle is defined. So putting these three ingredients together, the best push force from the wind, which is the flux, the total stuff that the sail catches, that's V A cosine of theta. If theta is 0, so that the normal to the sail and the wind are in the same direction, the sail is facing the wind, you have maximum effect. So when theta is 0, cosine has its maximum possible value. And so VA cosine theta, you may remember from physics part 1, in the case of work, this thing is called a dot product. So V dot A is a compact way of writing VA cosine theta. And so here A has been promoted to a vector, is basically the area, but you basically stick a needle or a pencil or something through this paper so that it's perpendicular. Normal means perpendicular, and then you want the normal, the thing that's sticking out from the paper, to be parallel to the wind, because that means the area is facing the thing head on, and that represents an angle of 0. So this concept of flux applies to many situations. For example, if you have these fish swimming like this, the density of the fish times how fast they're moving, that represents the field intensity of the moving fish. Now, if you have a net over here, for example, something like this, and you have this fish swimming in this direction, the bigger this net, the more likely you are to catch more fish. But also you want to orient it facing the fish. If you orient it like this, the fish will basically swim by and nothing's going to happen. So here's this net, that's the area, and you want to make sure that that area is facing the moving fish. So this again is a concept of flux. Instead of V that you had for in the case of the sail or electric field in the electric case, you have these fish that are moving. And then here you have a net that's basically facing this thing to catch the fish. It also applies to health sciences situations like neurotransmitter. There the presynaptic cell releases neurotransmitters. That's like a flux. The stuff is flowing everywhere, diffusing actually. On the postsynaptic cell, you have receptors. So those receptors are like this fishing net that I have over here. The more receptors you have, the more the area, the more neurotransmitter you're going to collect. So as you use your memory, for example, over and over again, that memory becomes more durable, more accessible. You increase the synaptic strength, and that happens by growing the number of receptors that you have on the receiving end. You're increasing the area, you're increasing the flux that you catch. So let's now do an example with the electric flux. So the same idea, just like you had this wind and the area, or the fish swimming and the area of the net and stuff like that, the electric flux, the symbol for which is phi sub E. Phi is the commonly used symbol for flux. Sub E indicates this is the electric flux. As you saw, your flux for neurotransmitters, fish, all kinds of other things, magnetic field and so on. So this is equal to E dot A, and that's EA cosine of theta, similar to what you had before. However, if the field is stronger, you have more of those electric field lines. If the area is bigger, you can catch more of them. You want the angle to be close to 0, so you have a head-on impact, you catch more of them. So this combination tells you how many of those electric field lines you catch, and this therefore is the flux. So here's an example. You have this racket that you saw before, and there's an electric field. This electric field has a value of 10 newtons per coulomb. And then you have this racket over here. It has an area of 0.025 meters squared. So that's this area over here. And then it's oriented at 20 degrees. So it's not facing head on exactly. It's off by about 20 degrees. The question is, how much electric flux do you catch? So this electric flux is given by this formula right here, EA cosine of theta. So you basically put those numbers in. So the electric field, as I mentioned, is 10 newtons per coulomb. The area is 0.025 meters squared, and the angle is 20 degrees, so you have cosine of 20. You crunch all that out, and this gives you 0.235. And the unit for electric flux, that's Newton meter squared per coulomb, because Newton per coulomb is the unit for the electric field, and area is just meter squared, and cosine has no dimension. Basically, it has no units. So this combination is Newton meter squared per coulomb, and that's how much flux you have going through this racket for this given electric field and given orientation. Now regarding this flux, something interesting happens if you have a closed surface. So this racket is not a closed surface. I mean, the fish could miss this and not get caught. But what you have a closed surface, if you enclose the fish with a completely closed fishing net with no holes in it. So let's look at what happened. So here you have a collection of fish. They're gathered for some social event like an anniversary or a birthday party or something like that. Once the party gets over, especially when the food gets over, all of these fish go their separate ways. They basically head home in all possible directions. So if you have a net around these, which is closed with no holes in it, you will catch all of the fish. If you have a bigger net, like this big net over here, the red or this pink net over here, it's bigger in size. It's also closed. You will also catch all of the fish. The point is, it doesn't matter whether this closed surface is small or big. As long as it's closed, it's going to catch all of the flux. So everything that is flying outwards, whether it's electric field, fish, mosquitoes, makes no difference. All of them are going to get caught. So you can relate the total flux caught to what is inside, and that can be used to calculate electric field. So in the electric phase, case, this is what happens. So here you have a bunch of charge stuffed into a small space. So this is a charge Q, the total charge Q over here. It is positive. So you have the electric field emanating and heading outwards. These are the field lines indicating the locus of each of the electric field over here. Then you have a closed surface, this one over here in green, a closed spherical surface. So the question, we want to relate the total flux that was caught to how much charge is inside. So to do that, this is an exact sphere. So the flux caught is E dot A, just by definition of electric flux. E is the field, A is the area. So in this particular case, the E is KQ over R squared, because this is a concentrated point charge over here. So as we saw from Coulomb's law, the electric field that comes out of a point charge at a distance r is KQ over R squared. And the area, because it's a sphere, the area of a sphere is 4 pi R squared. And then the angle is 0, because this is hitting the surface head on. So the normal to the surface and the direction of the electric field. So here's the area as a vector. That's the normal to the normal to the surface. They are pointing in the same direction. So this angle is 0. So when you put all this together, you end up with the electric flux for a closed surface, in this case a sphere, that's equal to 4 pi KQ enclosed. So you have a direct relationship between how much charge you have inside a surface and the total flux that's caught. Oftentimes there's another constant that's defined instead of K, the Coulomb's constant, which is 9 times 10 to the 9. There's another constant that's defined as epsilon 0, and that equals 1 over 4 pi K. So this is just another way of representing this Coulomb's constant. In terms of this, because epsilon 0 is 1 over 4 pi K, the 4 pi goes away. And now you can relate the enclosed electric flux to the enclosed charge divided by epsilon 0. Instead of multiplying by 4 pi K, if you use the epsilon 0, you end up dividing by epsilon 0. So it looks a little bit neater. And this connection between the enclosed flux and the charge inside, this is called Gauss's law. And we'll see what you can do with this Gauss's law. So it's like another representation of Coulomb's law. and gives you a way to calculate electric fields for complicated charge distributions. So here's an example that illustrates the use of Gauss's law. You're given a configuration of 3 charges. So you have a triangle of charges, a 3 coulomb, 1 coulomb, and -7 coulomb. You have a closed spherical surface. You have a closed surface enclosing these charges. And the question is to find the total flux that's captured by this closed surface for this triangle of charges. So from Gauss's law, we saw that the flux phi E for the closed surface, that's equal to 4 pi k Q enclosed. So Q is a charge within this closed surface. So now we just put the stuff in. This K over here, this is Coulomb's constant. It's 9 times 10 to the 9 from the earlier Coulomb's law. So 4 pi is 4 pi, K is 9 times 10 to the 9. The enclosed charge, that's the sum of these 3 charges. So it's +3, +1, and -7, which you have over here. And so when you crush, which is -3, so altogether you have a negative charge over here. And that gives you -3.4, 10 to the 11 Newton meter squared per coulomb. So this is the total flux leaving the surface. So notice that you have a negative sign. So the flux is actually entering the surface, because overall the charge inside is negative, it's not positive. Negative charges are like a vacuum. The electric field goes towards them. And so if you have a negative charge inside, the flux is going to be entering, not leaving. If inside you had a total net positive charge, flux will be leaving, because electric field lines leave positive charges and they enter negative charges. So here's another example of Gauss's law. Here we're going to use it to find the electric field outside a sphere of charge. Now in Coulomb's law, it was assumed that you had point charges. What happens if you have a charge spread over a sphere and it's not a point? Can you still use Coulomb's law to find the electric field outside? So we are about to show that yes, you can. So here's a point charge, and you have this spherical surface, closed spherical surface around it. Here's a spread out charge. It's not a point, it's a sphere of charge, Q sphere. But once again, you have this closed spherical surface around this charge over here. In both cases, you have an electric field at the same distance. So this R over here from the center of this point charge to the surface is the same as this R here from the center of the sphere to the surface. So the question is, how does this electric field caused by the sphere compare with the electric field caused by the point charge at an equal distance away from the centers of those 2 charges? So Gauss's law doesn't care how the charge is distributed inside the closed surface, whether it's a point, a sphere, or in the earlier example you had a triangle of 3 different charges and so on. Makes no difference. The flux, which is E dot A within a closed surface, is simply equal to 4 pi k times the charge enclosed. What the shape and size and distribution of the charge is does not matter. So in both cases, expanding upon this, the flux is E times A. The angle is 0, so the cosine is equal to 1. E is E over here. That's what you're trying to solve for. The area of a sphere is 4 pi r squared. On the right hand side, you have 4 pi k times q. The 4 pi's is going to cancel, so you're left with E equals kq or r squared. So this is equally true for both point and spherical distribution. So there is no difference. So this is the point. So if you have a sphere of charge, it behaves like a point charge. It's as if all of the charge was sitting at its center. So as far as electric fields outside, forces on other charges outside, a sphere of charge behaves exactly like a point charge for those calculations. And this is the proof using Gauss's law, basically. So we now come to the last topic in electrostatics, which is electric dipoles. So free charges are uncommon in nature. So any object you buy, like this pen over here, the net charge on this is pretty much close to 0. The number of the protons and electrons are equal. It's electrically neutral. It's rare to find something with a net charge, significant amounts of it. However, charge separation leading to a spread out charge distribution, a dipole, that's much more common. then even at the level of a molecule, quite often one side will be more positive and one side will be more negative. So a case in point, if you look at these two molecules like hydrogen chloride or water molecule, H2O, the hydrogen side is more positive. There's like a deficit of electron. The electron shift toward in the direction of chlorine over here. Here they shift in the direction of oxygen. Does the entire electron transfer from here to here? Well, not exactly. The H plus ends up with a positive charge, not of +1, losing the whole electron. It loses like a third of the electron, more or less. So it has a plus charge of 0.33 electron. And the oxygen ends up with minus 0.66 negative charge because it receives like a fractional electronic charge 0.33 from each of these things. But the point is that in this situation, even though the whole thing is electrically neutral, the charge is not symmetrically distributed. One side of the molecule is more positive and the other side is negative. This is what's referred to as an electric dipole. So the net force on a dipole is 0 because there's no net charge. You have equal amounts of positive and negative. They're just separated. So for example, in the case of the water molecule, the total force on the water molecule, that's coming from the force on the oxygen, the first hydrogen, the second hydrogen. So that electric force is given by the electric field times each charge. So that would be E times, this is minus 0.66, this is 0.33, and this is 0.33 times the charge for a single electron. And because the net charge is 0, this ends up being 0. So there is no net force on a dipole. However, there can be a torque. So to quantify the torque, to calculate the torque on the dipole, first we need to quantify a dipole. How do you measure the strength of a dipole? So that's a quantity called the electric dipole moment. So here it is. The symbol for that is P. That tells you how much charge separation you have, the quantity of the charge, and the separation distance. So here, this could be like a hydrogen chloride molecule or something like that. So one side is negative, one side is positive. The more the charge that you have that's separated, the bigger the dipole moment, the bigger the effect. Also, the greater the distance over which is separated, the bigger the effect. So these two things are captured in the definition of the electric dipole moment. The symbol is little p. That's equal to Q, the amount of charge that's separated, times D. So Q is the charge on one side, so don't take 2 times Q. If you have a plus 3 coulombs and minus 3 coulombs, Q is 3, not 6, basically. And D is then the separation here. So this is the electric dipole moment. Now once we have this thing defined, you can calculate the torque on the dipole in an electric field. So this dipole has now been placed in an electric field. Here's the E, the electric field, the light blue lines over here. As soon as you put this in an electric field, true, the force on this is in this direction, the force on the minus Q is to the left. These two are equal and opposite, the forces will cancel. But you'll have a twisting action here. So the top of this dipole is getting pushed this way, the bottom is getting pulled this way, so there's a tendency for the dipole to align with the electric field. This P, which is a vector here going from the minus to the plus charge over here, this wants to point in the same direction as E. So there is a torque. So to calculate the torque, you may recall from physics part 1, the torque is given by R cross F, RF sine theta. So here's a quick refresher of the business of torque. Let's say this is a tire. So you have a flat tire on the car, the tire is punctured, and you want to change it. So the tire is fixed using these little lug nuts, and then here's a wrench. You put this wrench around it, and you basically loosen these lug nuts over here. So this twisting action, that's the torque. It's like the force which is producing circular motion. So you can convert a force to a torque with a wrench like structure like this over here. So here's the force. This is the distance away from the point of rotation, from the pivot or the fulcrum. And we find that the greater the R is, the stronger the force. So if you're trying to loosen one of these things, having a short thing to rotate that is less effective than having something with a longer handle. The bigger the R, the more the torque. Then obviously if you apply a stronger force, you'll have a stronger torque. But the third thing is the orientation. You want to make sure you're pushing perpendicular to the direction of R. If you push like this, or if you pull like that, you will not have any rotation. You'll just be pushing and pulling. So to have rotation, the force needs to be perpendicular to the direction of R. Then you have the strongest effect. So the torque also goes up as the sine theta goes up. So when the theta is 90 degrees, you have the highest value of the torque. So combining these three things, you find that the torque is equal to RF sine theta. And this is kind of the expanded version of this compact notation, which you may or may not remember. The vector torque is R cross F. So this is a cross product. The value of a cross product is these two things, these two vector magnitudes times sine of theta. So this can now be applied for finding the torque on our electric dipole. So back to our dipole in the electric field. You have a plus charge, a minus charge is bathed in this electric field, this faint blue lines over here. And this electric field will push the positive charge away. It's going to pull the electric charge to the left, and that's going to cause the twisting action. So as we saw, the torque is RF sine theta in magnitude, but so the force in terms is Q times E. The force caused by an electric field is the electric field times the charge. But when you combine D and Q from here, that's the definition of a dipole moment, the charge times the separation. So combining the D and the Q, that's P, which is the dipole moment. So the torque of a dipole is the dipole moment P times the electric field times sine of theta. Now because of this torque, there's an energy associated with a dipole in an electric field. So let's say the electric field is pointing in this direction. The dipole wants to orient itself along the electric field. Why? Because the dipole, one end is negative, the other end is positive. So the electric field pushes the positive this way, it pulls the negative this way. So the dipole, if it's not aligned, there's basically a torque trying to align this thing in this manner. So if you basically applied a torque and moved it away from that, it's like tensing up a spring. If you let go, this thing will basically realign itself. So you have a potential energy associated with the dipole that's not aligned. So now what happens if you abruptly switch the direction of the electric field? Then this will be in a hurry to turn all the way around and face this direction. If you change the electric field again, this will rotate 180 degrees and go in this direction. So there's an energy associated with flipping the dipole completely from one orientation to the other orientation. And that energy, for flipping the dipole, U flip is 2PE. So P is the dipole moment, E is the electric field, and 2P is the amount of energy it takes to reverse the orientation of this thing, because it wants to always point along the direction of the electric field. So what happens if you abruptly change the electric field back and forth? This dipole is going to flip from one orientation to the other through 180 degrees. Each time the energy involved is 2PE. So if you're constantly reversing the electric field direction, this dipole will be flipping back and forth. There's friction between that and its surrounding, and that's going to generate heat. And that's basically how a microwave oven works. You have an oscillating electric field that's never making up its mind. It's always changing direction back and forth. And then this dipole is also trying to flip back and forth to keep up with the direction of the electric field. In the meanwhile, so polar molecules like water molecules, for example, food that have moisture in there, these things will be flipping back and forth. Due to friction, it ends up heating the food. So here's a demonstration of something similar. So this is a magnetic dipole. It's not an electric dipole, but the same idea. And here is a magnet. So I'm going to face this in a certain way. So notice that the dipole is aligning itself with the field. If I flip this magnet around, you see, this flips. If I flip it back again, it flips again. So if this thing is oscillating back and forth, every time this dipole is reorienting itself through 180 degree, and this back and forth flipping is going to generate heat. So this is a magnetic dipole, but basically the same thing happens in the case of an electric dipole.